Hello, welcome to chapter 22, amines. By the end of this chapter, we will be able to describe the structure of primary, secondary, and tertiary amines, assign IUPAC names for said amines, discuss the properties of amines, including their atomic structure, solubility, boiling point, odor, acidity, basicity, and describe the process of solvent extraction. Identify the reagents required to prepare amines from alkyl halides or carboxylic acids. Identify three methods for preparing an amine via a substitution reaction. Explain the process of reductive amination, including possible starting materials and reagents. Design a synthesis for a primary, secondary, or tertiary amine. Describe the reaction of amines with acyl halides, and explain why acylation of the amino group is a useful technique. Predict the products of a Hoffman elimination. Draw out the mechanism for the formation of a diazonium salt from a primary amine, or the formation of an N-nitrosamine from a secondary amine. Predict the products of the reactions of aryl diazonium salts, including azole coupling. Define the term heterocycle and discuss the structures and reactions of pyrrole, pyridine, imidazole, and pyrimidine. And lastly, describe the signals produced by amines in IR, proton NMR, and carbon-13 NMR spectroscopy. Let's start with a brief introduction. Amines are derivatives of ammonia and are designed as primary, secondary, or tertiary. We have here an example of a primary amine with one R group, secondary amine, two R groups, and a tertiary amine with three R groups. We also have, not as common, but we have quaternary ammonium ions. Amines that are naturally occurring are known as alkaloids. We have a few examples here. Some names that are fairly common, such as morphine, cocaine, nicotine. You can see the nitrogen, those amines are tertiary in many of these cases. We also have adrenaline, noradrenaline, and dopamine. So that means that they are very important towards our neurochemistry. Let's also talk a little bit about the shape of amines. As you know, shape will determine to a large extent behavior. The trigonopyramidal nitrogen atom of an amine carries a partial negative charge on its lone pair. We know that from our general chemistry. We have three bonds and we have a lone pair. It can function as a base. It can also function as a nucleophile. Now let's talk a little bit about nomenclature of amines. IUPAC nomenclature allows for two different ways of naming primary amines. First, we name the alkyl group ending with YL, followed by the suffix amine. So we have an ethane, two carbon atoms, so ethyl, right, YL, and then amine. We have an isopropanyl derived group, isopropane, isopropyl, right, YL, and then amine. Cyclohexyl amine. Right? So that's the first way in which we can name amines, very common. Second, more complicated primary amines are named as alkanamines. They are named the same as alcohols, but the suffix amine instead of OL, as you would with alcohols. So here, for instance, we have a 2R, 4R, 4,6-dimethyl, 2-heptane amine. So you name everything the same way that you have been doing so far, making sure that nitrogen is with the lowest possible number. That's where this 2 is coming from. And that's it, right? You end with amine. As you can see here, we can draw a bunch of analogies. We can draw that relationship with alcohols. So long as you rely on that, you should be okay. As an alternative, if you're using the amine group as a substituent in a separate group, for example, here we have an amine coupled with an hydroxyl of an alcohol. So in this case, what we do is that we use the term amino to specify that there is an amine, but that we're dealing with an alcohol primarily. Here, for example, on the example to the right, we have a benzoic acid as our main group. So we do use the word amino, and it is in the 1,4 position, or the para, so para-amino benzoic acid. If there's a case where we have an amine directly attached to an aromatic ring, then we're going to use the pair name aniline. So for example here, you can see the aniline group here, and we have a chlorine in the 1,3 or the meta position, so this will be meta-chloroaniline. And here, same situation, two substituents, 5-ethyl, 2-fluoroaniline. Now, in this case, we name the alkyl groups followed by the amine suffix. Use the di and tri if there are more than one of the same group. So we have an amine that is secondary, tertiary, for example. We want to be able to name every one of the substituents. So we have an ethyl, we have a methyl, and we have a propylamine. So we go by alphabetical order. Here we have two groups that are the same. So ethyl, ethyl, so diethyl, or trimethyl, and then the word amine. So in these cases, when we're dealing with secondary amines, we find the carbon parent chain and use the suffix amine, just like we did before. Smaller groups attached to the amine should be named as alkyl group with the N locand. So based on where that N, if they're attached to the amine, then N ethyl and methyl, currently what we have here. Now let's talk a little bit about the properties of amines. The nitrogen atom in typical amines is sp3 hybridized. I would expect a tetrahedral electronic geometry. It is close to 109.5 of that methane molecule. Because you have a lone pair, it's going to be slightly closer, right, slightly smaller. So 108 is typically the angle of those amines. The carbon-nitrogen bond length are approximately 147 picometers, which is a little bit shorter than carbon-carbon bonds, but longer than carbon-oxygen bonds, somewhere in between. Nitrogen atoms with three different alkyl groups are chiral. They possess four different groups, and the lone pair counted as a group. But usually we don't see optical activity in amines. So when we see the switch between the amine and its mirror image, we usually tend to see an intermediate that has a trigonal planar structure. So you can think of this as sort of like an umbrella going upside down and then right side up. And for that to happen, you need to have sort of an activation energy. In this case, it's going to be similar to 25 kilojoules per mole. Amines with fewer than 5 carbons are typically soluble in water. Primary and secondary amines can intermolecularly hydrogen bond and have higher boiling points than tertiary amines. So that hydrogen bond, I don't think we can overstate how important it is and how determinant it is in physical properties such as boiling points. You can see here, we're comparing a couple of groups here, oxygen with nitrogen, dimethyl ether, ethylamine, and ethanol. And you can see that the methyl ether only has one, actually has zero hydrogen bonding, no opportunity to hydrogen bond. The boiling point really low, negative 25 degrees Celsius. Here we have very weak opportunities for hydrogen bonds, so 17 degrees. Ethanol, very strong hydrogen bond opportunity here, so 78 degrees Celsius, even though they're all approximately, or they're actually the same molecular mass. Many small molar mass amines have unpleasant odors. Now that is definitely true. Rotten fish, that's the smell that you can associate with amines. We have putrescine and cadaverine. These are horrible smelling amines. And that is true of most. Every amine that I've run into always smells horrible. Amines are stronger bases than their alcohol or ether counterparts. They can also be readily protonated by strong and weak acids, mostly due to their lone pair, their ability to interact with other groups that way. It is useful to have a general idea of the pK values of protonated amines. So let's take a look at those. We have, for example, a couple of aniline derivatives with their conjugated acid and their pK values. You can see that they vary quite a bit. You go from weaker acidity at 6.2 all the way to 1.0, so very, very acidic in some cases. So that's a difference of 5, and as you remember, this is a logarithmic scale, so 5, that's 10 to the 5 now, so we're dealing with 10,000 times stronger. In general, amines with 5 or fewer carbons are highly soluble in water, while amines with more than 5 carbon atoms are slightly soluble in water. Solubility is enhanced in the presence of aqueous acid. Protonated ammonium ions are cations, therefore water soluble. And this is true of everything. If you add a charge to any compound, whether it's soluble or not, the solubility in water increases exponentially by having a charge. So that's basically what the second point is all about. Amines can be extracted from organic impurities using an aqueous acid and converting them to corresponding ammonium ions. Looking at the pK of most alkylamine conjugate acids, they lie between 10 and 11. Ariolamine are less basic than alkylamines. The lone pair is delocalized, as you can see here. You have delocalization that allows for a stabilization and less availability for protonation. Now, let's talk a little bit about how to prepare amines. There's a couple of ways that we've already gone over throughout this course. So let's do a quick review before we move on. First is preparing an amine from an alkyl halide and cyanide. Primary amines can be made from an alkyl halide in a two-step process. So we first add the cyanide ion, then we add an excess of our reducing agent, lithium aluminum hydrate, and water for those protons that we're going to need. And that would lead you to a primary amine, as you can see here. The carbon skeleton is expanded by 1. So that's one of the things that's unique about this specific reaction. Now, we can also start from a carboxylic acid. Amines can be made by converting a carboxylic acid to an amide, then reducing it with lithium aluminum hydrate. So we start with thionate chloride, excess of ammonia, and we convert that hydroxyl into a primary amine. And then we perform a reduction of this carbonyl with a strong reducing agent such as lithium aluminum hydrate and water. And now this one, contrary to the one we saw a slide before, this one doesn't really change the number of carbon atoms. Now we can also prepare aniline from benzene. So typically what we do here is through the nitration followed by a reduction. So we add a nitro group, then we reduce it into a primary amine. We can also obtain aniline derivatives from following the same process. So we start with a mixture of nitric acid, sulfuric acid, highly concentrated. We want to form those nitronium ions. Then we undergo the nitration. After that, we can do a reduction with hydrogen using a platinum catalyst, or we can go this route with an acid and a metal catalyst, followed by a strong base. That would leave you either way with the aniline. So now let's shift into preparation of amines through a different type of process. In this case, we're going to be talking about substitution reactions. Now, these reactions are very attractive for the formation of amines because we know that amines are very good nucleophiles and can easily undergo SN2 type substitution with an alkyl halide, similar to the one we have portrayed here. We start off with ammonia performing a nucleophilic attack. You would have an ammonium cation, which would then be attacked or deprotonated with the second ammonia, generating as a result a primary amine. This is a very efficient way to make quaternary ammonium salts. Monoalkylation is rather difficult because nitrogen becomes a better nucleophile as it picks up an alkyl group. So that means that for that first step, that's going to be actually the slowest at first alkylation. That second alkylation actually goes a little bit faster. So monoalkylation is a bit challenging to say the least. Now, let's talk a little bit about acide synthesis. That's the conversion of an alkyl halide to an acide, again following via SN2 reaction pathway. And after that, you have a reduction to yield a primary amine. So you have the sodium acide that you add to your alkyl halide. This is an example here. You end up with the acid substituents, which you can then reduce either with hydrogen and platinum, platinum being the catalyst, or lithium aluminum hydrate in water. That would yield that primary amine. This is a more efficient way to make primary amines rather than trying to monoalkylate ammonia. So if you're really sensitive about having primary amines, this is really the route that you should be taking rather than attempting to monoalkylate, adding some protecting group or whatever it is that might work in those cases. Now, let's take a look at the mechanism of that acid formation and then the eventual reduction. It starts off with a nucleophilic attack and the loss of a leaving group all at the same time. Remember, this is SN2 reaction, so everything happens in one step. After that, we have the acid group added to the alkyl, and we undergo a nucleophilic attack from the reducing agents. You have the lithium aluminum hydride attacking that lone pair of the acid, that first nitrogen, the one closest to the alkyl group. After that, we see the loss of a leaving group, this right here, nitrogen gets lost, and eventually we get a protonation to charge stabilize the whole thing, and you end up ultimately with a primary amine. Now, let's talk a little bit about a very specific type of reaction. We call it the Gabriel synthesis. It is the synthesis used for primary or secondary amines from phthalamide. Phthalamide is this molecule right here. And the way we sort of make these primary secondary amines, we first add a strong base to sort of deprotonate right here. That will give you the phthalamide anion. After that, you have potassium phthalamide. It could be sodium phthalamide, it can be whatever counter ion we need at a specific point. We can then proceed to alkylate this anion or this nucleophile and add whatever R group we need based on whatever specific need we have. This undergoes an SN2 type reaction, and you end up right here with a tertiary, in this case, amine. Once we're there, we're at that point, we have that R group added. We are down to our last step, which generally employ aqueous acid or hydrazine to liberate the amine, to break it off. So adding that acid, basically what it does is that it oxidizes here, and that N R group becomes protonated. You have the cation of the amine that you're expecting, or the primary amine that you're expecting to recuperate later. In this case, we actually have hydrazine here, and here what would happen is that instead of oxidation, you actually have sort of a nitrogen in that step. However, the angle, as you can see, is basically the same thing. You end up with that nitrogen, with that R group. In this case, you have a plus charge, so you're going to have to charge balance that, probably neutralize the reaction to lose that extra proton. In this case, you actually don't have to do that. Now, another thing we can do reductive amination, and that is when we have a ketone or an aldehyde, and I believe we saw that in the last chapter. We can convert it to an imine, which is then reduced to the corresponding amine. So in this case, in the presence of an acid, we're dealing with a ketone first, could be just as easily an aldehyde. We're actually talking about the carbonyl. Ammonia, in the presence of acid, you form the imine group right here, which can then be reduced. So this double bond becomes a single bond, then another hydrogen. For that, you need an excess of hydrogen. If a reducing agent is present, the imine can be reduced in situ to form an amine. So you don't really need to undergo any type of filtration or other changing experimental conditions. Reductive amination can be accomplished with a variety of reducing agents. So let's talk first about sodium borohydride. It's commonly used because it is selective for imine, the sodium cyanoborohydride, which is an analog, right? This analog is the one that we tend to use rather than the generic sodium borohydride. And that cyano group, the cyanide ion, is what makes it selective for imines. Since sodium cyanoborohydride does not react with ketones and aldehydes, it can be used in situ for imine formation, and it will yield the desired amine in a one reaction synthesis. That's actually very attractive because, as you saw before, most of these reactions involve more than one step, which, if you translate from the slide into actual experimental conditions, usually implies more than one setup, filtration, purification, which is very time consuming. So this actually takes care of all of that. Now, another advantage of reductive amination is that it can yield primary, secondary, or tertiary amine based on the amine that you're adding into your ketonaldehyde synthesis system. Overall, there are three options to produce primary amines. We can go the potassium phthalimide route, we can go the sodium acid route, or we can go the ammonia route. It really depends on what exactly you plan to do, what are your requirements, purity, time, etc. Primary amines can then be used to obtain secondary, tertiary amines. So once we obtain that primary, we purify, we isolate, we can then move on to generate secondary and tertiary amines. Now let's talk a little bit about acylation of amines. Recall that amines are converted to amides with an acyl chloride, and we saw that I think it was last chapter. 2 moles of amine are required, and we know that acylation of an amine can be used as a protecting group. Consider how to perform monobromination of aniline. If aniline is directly brominated, polybromination is observed. That means that just having the benzene by itself is not going to generate anything really. But if you have that amine group, you now have aniline, and when you add an excess of bromine, then you get bromine in the ortho and para positions. The amino group is too powerful of an activating group. That's the consequence, or basically the takeaway point from this slide. So what does that mean? The amine group must first be protected, so we turn it into an amide, and then we can undergo bromination, especially if we're just looking for bromination to happen in just one place, in this case the para position. Now in this case, when you add this group right here, what will happen is that you will have bromine added to the para position, but also bromine added to the ortho position, but in much smaller quantities, so 5% or less. Now as you can see, this you don't have bromine here or here. So what that means is that the amine, when turning into the amide, it actually sort of calms down or makes it more mild as an activator, allowing for the para position to sort of predominate, and that's where you'll be getting that bromine added. After you do that, then you take the amide and you turn it back into the amine, and you're good to go. Now, the problem or the challenge with this route is that when you form an amide and you need to hydrolyze, then that requires pretty hostile or harsh conditions. Aromatic amines also cannot undergo Friedel-Crafts directly. The amine reacts with the Lewis acid catalyst, and you end up with an adduct that you really don't care for if you're trying to undergo Friedel-Crafts. And not just that, but you have a deactivating sort of effect once you go this route. So to achieve ring alkylation, we must first acylate the amine, and then we move forward. And like what we see here, we have the amine, we have the acyl group. Once we do that, then we perform whatever reaction we're looking to perform in the ring. In this case, we're adding a methyl group in the para position. Once we do that, then the acyl group goes away, and it becomes an amine group. Now let's talk a little bit about Hofmann elimination and how it applies to amines. Just like with alcohols, amines can serve as precursors for the synthesis of alkenes via an E2 elimination. So this is just a reminder to sort of go over your alcohol chapter, like we've already seen at the beginning of the beginning of OCHEM 2, the end of OCHEM 1. So there's a lot of analogies. If you recall those mechanisms, then this one should be fairly simple. Now, adding an excess of methyl iodide will convert an amine to a quaternary ammonium salt, which actually serves as a very good leaving group. Strong base would then cause the E2 elimination. Silver oxide is commonly used in these cases. Now, that entire process is known as a Hofmann elimination. Hofmann eliminations give the terminal alkene regioselectively. So it's not going to be the substitute, it's going to be the terminal. Sterics in the anti-coplanar conformation hinders attack at the more substituted site. So in other words, because you have that quaternary um, ammonium salt, that actually sort of forces the reaction to go this route, or the attack to go this route. And that's why you get a carbon in the terminal side rather than on the more substituted. Now, nitrous acid is unstable and must be generated in situ in order to react with an amine. Nitrous acid loses water to form the active electrophile and nitrosamonium ion. Now, sodium nitrate in the presence of hydrogen chloride or hydrochloric acid, really, it will protonate, so in acidic conditions. After that, you have nitrous acid, which will then protonate once again, forming, we have an oxonium ion here, which you then lose, and that will give you the nitrosonium ion. Now, when we're talking about reactions with secondary amines, you will end up with N-nitrosamine. That will be the nitro, and then the N-nitrosamine. So in the end, it's gonna dash. The way that works, the mechanism is a nucleophilic attack followed by a deprotonation. So we have the nitrosonium ion. It gets nucleophilically attacked by the secondary amine, and after that, then we get a deprotonation step. Nitrosoamines are known to be potent carcinogens. There's a number of molecules that we know to be carcinogens, usually flat molecules, halogenated molecules, things of that nature. Nitrosoamines are on a family of their own, but they're also very strong carcinogens, so we tend to sort of avoid them if we can. But in many food products, especially processed foods, you are going to find them. So, for example, in bacon, you see nitrosopyridine, nitrosonornicotine. You find it in tobacco smoke. In some food products, you see nitrosodimethylamine. It's just byproducts, right, of processes of preparing foods, and we do find them, albeit in trace amounts. I will say that. Now, the nitrous acid reaction with primary amines will yield a diazonium salt. Right? Azonium, right here with that plus charge, that will be the salt. This is a process known as diazotization. So the mechanism is a multi-step. You have the nitrosonium ion first. Once you have that formed, it undergoes a nucleophilic attack, similar to what we saw before, followed by a deprotonation. Once we have that, then that oxygen becomes protonated. You can see the attack here. And we lose a proton on the amine group, followed by another protonation on oxygen. Once you have that, you have the oxonium ion, which is a very good leaving group, and your final product. Now, there's another reaction known as the Sand-Meyer reaction. It is a reaction of an aryl diazonium ion with a copper salt to install a halogen or a cyano group in the ring. So depending on what halogen or if it's a cyano, then you go with either copper bromide, copper chloride, etc. And that's how you end up with that halogen or that cyano group there. Overall, the Sand-Meyer reaction is part of a multi-step sequence to install a carboxylic group on a benzene ring. Aryl diazonium ions also serve as precursors for installing a fluorine or a hydroxyl group on a benzene ring. So these are many purposes. As you can see, most of them are going to be as precursors for other reactions, for other groups that we need to add. Once we have these groups, then we can further functionalize or whatever it is that we need to do. The diazonium ion can also be replaced with a simple hydrogen, then you go back to benzene. This is useful when an amino group is needed on the ring temporarily to take advantage of its activating or directing effects. So for example, we form aniline. Once we do that, we brominate, and we actually have bromine on these three positions, but I really don't care about this amine group. Well, in that case, I can undergo a nitrosonium ion reaction um, followed by the replacement of that diazonium ion with a hydrogen, and that's it. Lastly, diazonium salts also serve as electrophiles and are attacked by activated aromatic rings. This is known as an azo coupling. Now let's talk a little bit about nitrogen heteroaromatic compounds. As you know, we've seen a few of these before. We have heterocyclic compounds, which is a cyclic compound that contains elements other than carbon and hydrogen. So in this case, we have a couple of examples of rings that contain nitrogen instead, or in addition to your carbon atoms. So pyrrole is a simple aromatic heterocycle and it undergoes electrophilic aromatic substitution, and it does so much faster than benzene. Substitution at the carbon number 2 will give you the most stable intermediate. So we have the resonance stabilized intermediate followed by the loss of a proton and the halogenation at that position 2, or that first position actually, gives you that brominated compound. Imidazole is also an aromatic heterocycle and is found in naturally occurring compounds such as imidazole and histamine. Pyridine is a 6-member heterocycle. Let's see the nitrogen on this side. The lone pair of nitrogen is not delocalized, so that makes it a weak base. Pyrimidine actually is similar to pyridine and is a common moiety in biological molecules. So this is actually a piece of a large molecule that you see in many cases in biological systems. Both pyridine and pyrimidine can undergo electrophilic aromatic substitution reactions. However, their yields tend to be fairly low. Now let's talk a little bit about spectroscopy of amines. Amines generally give broad infrared peaks between 33 and 3500 centimeters to the -1. They tend to be a lot less intense than that hydroxyl stretching that we tend to see in infrared. Primary amines will give you 2 nitrogen-hydrogen stretch signals. Secondary amines will give you just 1, and tertiary amines will give you no NH stretch signals. Now talking about proton NMR, nitrogen, hydrogen, that NH bond or that proton generally appears between 0.5 and 5 ppm in proton NMR. Where exactly in that range? Well, it depends on the type of solvent, the concentration, and the temperature. Because these protons are generally exchanged at a faster rate than the NMR timescale, then these protons usually provide broad signals with no splitting. If we use deuterated solvents, then that nitrogen-hydrogen proton peak disappears completely. Now let's talk a little bit about carbon NMR. Proton adjacent to nitrogen typically show up around 2 to 3 ppm. Carbon atoms bound to nitrogen typically appear between 30 and 50 ppm. Compounds with an odd number of nitrogen atoms will have an odd mass molecular ion in the mass spectrum. Amines also typically undergo alpha cleavage in the mass spec, giving predictable mass patterns.